Okay, so now we need to construct a 95% confidence interval for the proportion of red beads based on our sample. So the formula for that was back here on this blue box a couple pages ago. There it was. P hat plus or minus C alpha over 2 times the square root of all that stuff. Okay, so I wrote that down. There's the formula part right here, right there. And then you want to substitute into the every aspect of that formula. So you say, okay, p hat in our example was 0.25. So you put 0.25 in there. And then p hat over here is 0.25. 1 minus 0.25. N was 120. That was how many beads there were in our sample total. And now where does the 1.96 come from? Well, that comes from the fact that we said it was a 95% confidence level. And over here we learned that 95% confidence level is 1.960. Okay. Okay, so we could find those values with a calculator. I mean, you just take a calculator and type 0.25 minus 1.96, blah, 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 0.25 plus, etc. But where's the fun in that? We want to find it the fun way. We're going to use Excel to do this for us and StatCrunch. So we could use Excel, honestly, just as a glorified calculator. So you could say, you know, the lower limit is equal to, and now it was 0.25 minus 1.960 times SQRT, the square root of, and it was 0.25 times 1 minus 0.25 divided by n, which was 120, and close your parentheses. So that's your lower limit. And then for the upper limit, it's the same thing, but with a plus sign in it. And you don't have to do it all in one either, like I just did. Oh, I better label this. This was 9.1 example. Let me go back here. Oh, these are different. You know what? I better put this on its own thing. So I'm going to cut these out of here. Paste them in here. Okay, so this one was 9.1 example 3. That was finding those z-scores. And this is 9.1 example 4. So we could find it that way. And again, you don't have to do it all in one fell swoop if you don't want to. You can take the time to put in what p hat was, which was 0.25, and then n was 120. And you could use some cell referencing instead. You could say, okay, I need p hat, which is here, equal to that number minus 1.96 times SQRT, parentheses, that number times 1 minus that number, close parentheses, divided by n, which was 120, boom, right? And then you're kind of using cell referencing to help yourself. Oops. Except you want that whole thing. Don't drag it if you want to find the upper limit. If you drag it, it won't work because everything has changed. You want to kind of go in there and copy and paste or just retype the whole thing, but with a plus sign instead. Well, that's kind of cumbersome, to be honest, because Excel is making us do this longhand. So there's got to be a better way, right? And let's go to StatCrunch and see if we can find that better way. So here I am with StatCrunch. My StatCrunch open. All right, let's go to Stat. And we want to go to Proportions down here, Proportions, one sample. And we have summary statistics, like we didn't sit there and count. So we were told X was 30 and then N was 120, so we're going to use that fact. Okay, so the number of successes, that's the number of red beads in our scoop, that was 30. The number of observations total, that's 120. This is X up here, and this is N down here. Click Next, and it's going to ask you what you want to do. Do you want to do a hypothesis test, which is Chapter 10, or a confidence interval? We want a confidence interval. What confidence level do you want? Well, we want 0.95, and we're going to do the standard walled. So we'll just leave it like it is and click Next. Do you want to store your output in a data table? That'll put it in here, actually, which you can do or not do. I don't really care. I'm going to click Calculate. And there it is. So I can copy. Oh, thank goodness for old school copy and paste. So copy, and you can just paste it right here. And there it is. It's much faster, actually, than Excel is. It's totally fine to find it with this way. Or again, if you have the formula, you can just do it yourself longhand with a calculator. All right. Notice, by the way, that StatCrunch tells us 0.25 right there. It also tells us the standard error formula, in case you wanted to know. That's the square root part with the p hat and the 1 minus p hat. All that good stuff. Cool. All right, so I will copy and paste this back in to the notes. So we have that, and then the interval itself is those two numbers. Let me get down here. Okay, it's equal to 0.1725, comma 0.3275. Or if you like, if we want to round, 0.173 to 0.327. Does that sound familiar? Good, because it should, because it's the same interval, hold on, that we found way back here. I said when we first built this that the confidence, right here, 17.3% to 32.7%. Look at that. Just like we said. Cool. All right, so you've made your first confidence interval. I hope you enjoyed it. Formula, substitution, final answer. How you choose to get your final answer depends on what you're working with. StatCrunch is super easy to use. Don't forget that p hat, your sample proportion, is equal to x over n. And the x and the n part are actually whole numbers. They have to be whole numbers. And if you're using StatCrunch, which is really nice and easy, make sure you remember that. You can't put in decimals for those values. They have to be whole numbers for both of them. N, by the way, is always the bigger of the two numbers. So if you're looking at them and you're thinking, oh, which one's 30 and which one's 120, the bottom one has to be the 120, has to be the larger of the two. All right, now how do we interpret that confidence interval? Well, the way we interpret it is we say that we are 95% confident that the true proportion of red beads in that box is between 17.3% and 32.7%. It's not a probability. You're not talking about the future. You're talking about how confident you are that your sample captured what was truly happening for the population proportion. Right? Now, what's our point estimate for the true proportion of red beads? That would be our sample proportion, which was equal to p hat, right? And p hat was equal to 0.25. We knew that already anyway. It was, oops, here I can even give you the fraction. It was 30 over 120. But in case we had forgotten, StatCrunch found it for us anyway. It tells us it's right here, right? There's the sample proportion, like that. So that's p hat. That's your best guess. That's the center of your interval. Now, what was your margin of error? Now, I know it was 7.7% because we found it before, but how will we find it now? Well, you can do this two ways. So let me insert a table here. We're going to do it the quick way, the easy way, and the formula way. How about this way? The short way and the long way. The long way. Okay, so the short way is saying, look, I know that the interval is 17.3%. Here, let me do it this way. 0.173, comma, 0.327, right? And I know the point estimate, which is the center of the interval, is 0.25. So to find the error, all you have to do is take 0.327 minus 0.25, and you're going to have, lo and behold, 0.077, which is what we said it was way back. Okay, now, why am I doing it that way? Well, don't forget your picture. Let me go back and grab it. Way back here. Right there. So you say, look, if this is 32.7 over here, and the error is the distance between that outer edge and that center, that point estimate, all you have to do is subtract. 32.7, take away 25, you're going to have 7.7, right? And same thing with the other end. This was not the only way I could have done this. I could also have found it by subtracting. Hold on, let me put this in here real small. You could also find it by subtracting that middle value, 25%. 0.25, take away 0.173, whoopsie, and you're still going to get 0.077. Now, the long way to do this is to use the formula. Now, you don't always have to. I mean, if I give you the interval ahead of time, or let's say you're on a test and the interval is just pre-given, or you're just looking at the StatCrunch output given to you. Like on a test, I just give you this little picture right here. And you could figure out the margin of error from that. All you'd have to do is subtract, right? But if that wasn't what you were given, then you still have a formula for the margin of error. It's z alpha over 2 big square root, and then it was p hat times 1 minus p hat all over n, like this. Okay, well, we learned that that was 1.96 times the square root, and then p hat we know is 0.25 times 1 minus 0.25 divided by n, which was 120. And you could sit there and do it longhand with a calculator, in which case you're going to come up with the same thing as we did before, 0.077. So I know it seems like the short way is actually longer in terms of how much we typed, but that's just to explain what's going on. In the end, it's a much simpler calculation to do a simple subtraction than it is to do this big honkin' formula, because you got to find z alpha over 2, which you got to figure out that that's 1.96 this time, and then you got to put in your p hats, and you've got to divide everything carefully with your square root symbols and all that stuff. All right. Now, if we increased our margin of error, how would that, if we increased our confidence level, how would that affect our margin of error? And that's assuming, by the way, that everything else is left the same, assuming sample size and n is left the same, and is left at 120. Just on a side note, because you could always increase your sample size, and that's going to affect things as well. But we're going to assume that we're still sticking with the same little scoop of 120 beads. If you want to increase your confidence level, what's that going to mean for your margin of error? Okay, well, if you increase your confidence level, here, let me type this up, hold on. All right, if we increase our confidence level without changing our sample size, then the interval is going to get wider, which means the margin of error is also going to get larger, because remember that your margin of error is equal to half your width of your interval. We learned that way back here. Oops. Well, this will work. Right? There's the width is the orange, right? Or the yellowish color. So that's the whole interval. So the error is half of that. So if you want to be more certain you caught it, you can make a bigger interval, and that's going to mean automatically that your margin of error is getting larger, right? Where the width of the interval gets larger, the error gets larger. So if you increase your confidence, you just want to make it so you're more sure, but you don't change your sample size, so you're still working in this little Dixie cup scoop, then that's going to mean that you're going to have a larger error. All right, we're done with that section, and we will move into Objective 3, determining the sample size needed. I'll see you back here for them.